Okay, so here's our video for chapter 4.2. What we're going to do is we're going to practice 6 problems from the course review found in your book on page 510. We're going to start by looking at number 13. It says, write each equation in its equivalent exponential form. So you must go from the log form to the exponential form. So let's remind ourselves how that property looks. So we have log base b of a equals c. Well, to go to exponential form, it becomes b to the c power equals a. So the base to the value equals the argument. 1 second. So base to the value equals the argument. Okay, so let's see here. Well, the base is 49, so I have 49. The value is a half to the half power equals 7, and that's exponential form. Let's look at number 17. Now it says write each equation in its equivalent log form. So now you want to go from your exponential to your log. So I have b to the 4th power equals 625. So remember, that's the same as saying base to the value equals the argument. Base to the value equals the argument. And I need to write it in log base of something, log base b, where is that? Log base b of the argument equals some value. Okay, so log base b of 625, let's make my b look like a b, equals 4. Good. So recap, going from log to exponential, and then from exponential to log. Make sure you're using these equivalent formulas. Okay. Log base b of a equals c is the same as saying b to the c equals a. Great, now let's move on down to number 26. Hold on for a second. My b is looking like a 6 to me, so let me fix that. That should be log base b of 625 equals 4. Alright, now let's go down to number 26. It says evaluate each expression without using a calculator. If evaluation is not possible, state the reason. So I have log base 3 of 1 over the square root of 3. Okay, I'm sorry for that. Log base 3 of 1 over the square root of 3. So let's see here. The first thing you gotta do is you want your base and argument to be equal. So you want your base and your argument to be equal. And let me remind you of the property. Log base b of b to, let's say, some a power is the same as saying a. When the base and the argument are equal, they basically cancel out and you're left with just the power. Okay? Now notice that my argument, this b right here, he's in my numerator. There is literally no fraction here. I have a fraction in this problem. So the first thing I want to do is rewrite the square root, and then I want to take the 3 and move it from the denominator to the numerator. So let's first rewrite the square root. That's log base 3 of 1 over 3 raised to the 1/2 power. Remember, the square root is the same as saying a half power. And again, let me remind you of that property. So if I have, let's say, x to the a over b, where this is the power, is the same as saying the b root of x to the a power. Okay? So in this case, we have the square root of 3. The power on the inside is a 1, and since it's a square root, the power on the outside is 2. So that's the same as saying 3 to the 1 over 2 power, 3 to the 1/2. Great. Now our next step is to move it from the denominator to the numerator. So move it from the denominator to the numerator. Let me remind you of another property. There's many properties here, right? There is the property x to the, let's use a power, I'm sorry, shoot, hold on for a second. Let me get an eraser. Okay, where's my pen? X to the a power is the same as saying 1 over x to the negative a power. As well as, here's another property, 1 over x to the a power is the same as saying x to the negative a power. So basically all we're saying, if you move the base from the numerator to the denominator, you're changing the sign of the power. That's it, just the sign. And if you move the base from the denominator to the numerator, you're still just changing the sign of the power. So if I take this base of 3, and remember when I'm saying base, I'm not saying log base, I'm just saying base. This comes back from our regular algebra terminology. If I take this 3 and move him from the denominator to the numerator, the only thing that will change is the sign of this power. So this is the same as saying, let's use a different color. Log base 3 of 3 to now the negative 1/2. Okay? If I take this 3 and move him from the denominator to the numerator, the power stays the same, except for now the sign changes. So he was positive down here, he's negative up there. Great. Now we have it that my base and my argument are exactly the same. So in essence, they cancel out, and I'm only left with just the power. So this answer is 1/2. So log base 3 of 1 over the square root of 3 is just 1/2. Okay, let's keep going. Now let us look at number 41. I skipped over the graphing because we can now do graphing with our calculators, and the transformations, all that you can confirm with your calculators. So number 41, it says find the domain of each log function. F of x is equal to log base 8 of x plus 5. Log base 8 of x plus 5. It says find the domain. So again, let's recap that the domain are all the x values that make this function valid. And when I say valid, I basically mean work. Like if I plug this x in, it will give me something back. Okay? So a characteristic of all the logs, your argument, the thing you're taking the log of, okay, the argument must be greater than 0. Must be greater than 0. So this argument is x plus 5, is log base 8 of x plus 5. So whatever follows the word of, that is your argument. So x plus 5 must be greater than 0. Therefore, now let's solve for x. Subtract 5 on both sides. X must be greater than negative 5. That's your domain. X must be greater than negative 5. We can draw a number line, put negative 5 on it. It says greater than, so I must be open a parentheses to the right. And then I will shade all of this. And of course, this will go on until infinity. So the interval would be negative 5, parentheses, negative 5, comma, infinity. That's the domain. And of course, you can pick a number in this domain like 10. Like 10, and you can plug it in. 1 second. Okay, so like 10. Log base 8 of 10 plus 5 is log base 8 of 15. Now, I can't calculate that with my calculator, but I can trust it'll give me an answer because the argument is positive. Okay? And remember, you're using a parentheses, not a bracket, because you were not including the negative 5. You cannot take the log of 0. And if I put negative 5 in for x, I'm going to have log base 8 of 0. It is undefined. You cannot do that. Therefore, use parentheses. Alright, let's continue finding domains. Let's work on number 42. So now I have f of x is log of 3 minus x. F of x is a log of 3 minus x. I do not need to remind you again that the domain means the x values and that the argument has to be greater than 0. So let's just work it out. So I'm going to add x on both sides. Remember, it doesn't matter which piece you move when solving for x. So I added x on both sides, and I ended up with x is less than 3. X is less than 3. So x is less than 3. Draw a number line. Here is the 3. He is less than, so he has the parentheses open up to the left. And I shade all of this to the left. And it's going off to negative infinity. So your interval is parentheses negative infinity, comma 3 with a parentheses. And of course you can pick a value from here and check it. So like, I don't know, negative 5. He lives here, right? So 3 minus negative 5 becomes the log of positive 8. And of course we can use a calculator for that, but the whole point is that the argument is positive. Okay? Alright, one more to look at. Now this one is actually very interesting because it takes you back to some things that we need to remind you of because your final's coming up anyways. So number 43, it says f of x is equal to the natural log of x minus 1 whole thing squared. Well, the log and the natural log, they have the same characteristics. If the log's argument has to be positive, then the natural log's argument also has to be positive. Basically, greater than 0. So go ahead and set your argument greater than 0. So we have x minus 1 whole thing squared is greater than 0. Now I need to get rid of the square root, right? So take the square on both sides, take the square on both sides, and I have x minus 1 greater than 0. Let me pause for a second. 1 second. I take that back. Let me come back. Let me come back. Let me explain this away. Let me explain this another way. Okay, this one is interesting because the argument is x minus 1 squared. And he has to be greater than 0, correct? But isn't the square telling you that this thing is always going to be positive? Always going to be positive. And it should remind you of the polynomial inequalities that we worked before. This is a polynomial inequality. If I was to multiply this out, I would have x squared minus 2x plus 1 must be greater than 0. Okay? This is my polynomial inequality. Because this square is here, this is always going to be positive except when x equals 1. Something happens when x equals 1. When x is equal to 1, this thing on the left side, this thing on the left side becomes 0, which is not okay. So basically, x can be everything except for 1. Now, I am trying to explain that logically to you, and hopefully you're understanding. If not, you will have to solve this like you solved the inequality, the polynomial inequalities from before. So again, x minus 1 squared greater than 0. Well, I'm not going to, the first thing we did then, you had to set your polynomial equal to 0, correct? And then you solve for x. So you take the square root, and you have x minus 1 still equals 0. So x equals 1. This became your boundary point, if you remember. This one is an interesting problem. So you have this boundary point, and he's 1. And remember, you open a parenthesis facing to the left and to the right. And what you did is you picked values out of here and plugged it right back in there to see if they gave you the positive or the negative. So let's pick 0. He lives over here. 0, let's do it above here. 0 minus 1, whole thing squared, is going to become positive. Then you pick the value from over here, like 10. And you plugged him in. 10 minus 1, whole thing squared, well, that's positive as well. So basically, the answer to this is everything except the 1. So the domain of this natural log is negative infinity to 1, union 1 to infinity. Okay? So let's recap that. The argument has to be positive, greater than 0. Because there is a square right here, this argument is always positive except when x is 1. Therefore, he must not be included in your domain. Every other x is there except this one, basically when x is 1. If that doesn't make sense to you logically, then you must work out the polynomial inequalities that we learned from before. And 1, x equal to 1, becomes a boundary point, and then you test values to the left and to the right, and you'll see it's always positive except when x is 1. So he's not included in your domain. Okay, that concludes chapter 4.2. Let me know if you have any questions.